Okay, a quick introduction to phasor diagrams and their use in analyzing LRC circuits. You recall in lab we used the switching back and forth with a wiring diagram that you eventually figured out, some quickly or a little more slowly. Good exercise anyway. But using a battery, we were able to achieve a square wave. Now actually, the current is here, then it's here, and it really doesn't do anything in between, because as soon as you cut off the switch, the current stops. So this vertical line really shouldn't be there in the square wave, but that's the way we draw it anyway. Really nothing is happening between here and here. And this starts essentially instantly after this one ends, even though there is a delay, so really it isn't perfect. But we draw this vertical line anyway for reference. Okay, well, what happens if we have a capacitor in the circuit and we have some resistance? Battery has resistance, if nothing else. Well, if we start, let's say here, with a capacitor uncharged, the capacitor voltage, which we'll designate by V sub C of t, starts at 0 and begins to approach exponentially this voltage here. And it continues happily doing so, but pretty soon it gets cut off. So now it's got to exponentially approach this voltage. Well, what's it do? Well, it's going to very quickly reverse, and probably doesn't get that close to the voltage. My time constant here would not match my time constant here, so I didn't draw that very well. But I leave it to you to think of how that really could be done a little better. It's really going to come down maybe to here, and then it's going to go up maybe a little closer. And you can work that out just using the exponential equation. But the qualitative idea is that your current is going to your capacitor voltage, every time you reverse the voltage, it's going to exponentially approach that new voltage. So you have a series of exponential approaches cut off at a certain time. Okay, so that the capacitor voltage reaches 0 later than the source voltage reaches 0. So there's a phase lag between the capacitor voltage and the source voltage. Okay. So phase lag between Vs and Vc, where Vc, voltage across the capacitor, reaches 0 later than the source voltage. Now, the source voltage obviously reaches 0 when you throw the switch. And then when the switch makes contact, it almost instantaneously comes down to its lower value. Okay, well, there's a phase lag between Vs and Vc, and that phase lag, we could say, would correspond to, that's not a good way to draw that, would correspond to this little interval here. Now, what we're more interested in is the phase lag between the capacitor voltage and the current. So we want to think about that. So what happens to the current as all this is going on? Now, as you experienced in cranking the capacitor, the generator with the capacitor, as the capacitor voltage approaches the source voltage, well, the capacitor voltage opposes the voltage of the source, which results in less and less current. So the current exponentially decreases. It's maximum here, and it exponentially decreases until the voltage is reversed. So we'll figure out what happens when the voltage is reversed, but we can see that we're going to have a exponential decrease in the current. So the current is going to be I of t, and I'm going to use yellow to label that, and yellow to indicate this curve. okay, the current curve. Now, what happens when the capacitor voltage reverses? Well, the capacitor, what happens when the source voltage reverses? Well, the capacitor is already pushing in the direction of this reversed voltage, so that you have the voltage of the source now reinforcing the voltage of the capacitor. So they're working together, and you're going to pretty much instantly, you're going to get a sharp drop in the current. So the current is going to go down very quickly, almost instantaneously, down to some low value that's much greater in magnitude than the positive value you had here. And you experience that when you reverse the cranking. All of a sudden, the cranking gets really difficult. The mechanical resistance increases in a surprising way, a way that is surprising if you don't already know what to anticipate. So that your capacitor current will go down to some value here, okay? Then what's going to happen? Well, the source voltage remains what it is. The capacitor voltage, which is opposing the source voltage, decreases. Well, in this case, the capacitor voltage is still reinforcing the source voltage, but at a decreasing rate until you get to here, and then it begins opposing the source voltage. And you can feel the cranking getting easier, and it kind of gets rapidly easier, so that what happens is the current in the circuit, because of the first decreasing and then opposing capacitor voltage, is going to exponentially approach zero once more. It's not going to have time to get as close to zero as it was over here, but it's going to exponentially approach zero. But now you reverse the current again. You have all this capacitor voltage here resisting the increase. And so you have all the capacitor voltage reinforcing the new voltage of the source. And you're going to, again, spike up here. And then the voltage of the source is going to exponentially approach zero until you spike down here again, and so forth. Now, this is a qualitative picture. There are subtleties of the process that I haven't addressed. In other words, is this spike higher, further from the zero current than this one? In other words, is this distance greater or less than this distance, and so forth. And again, you can kind of think that through. You can actually do that analytically using the exponential functions. And of course, you could analyze this circuit using Laplace transforms for the step function. You can't do just straight derivatives of the step function to get a nicely behaved differential equation. Your driving voltage is not a nice function, so you can't use the methods, for example, variation of parameters and or undetermined coefficients it would use in solving a non-homogeneous differential equation. Still, you have these relationships, and what we can see here is that there's a phase lag also between the current and the voltage. The current is going to reach zero before the voltage does. So current reaches zero here, voltage of the capacitor reaches zero here. So there's a lag between the two, and we want to talk about how to do that with a circular diagram, which is very much the same type of diagram that we use in modeling simple harmonic motion with a reference circle, something you should be very aware of. You should review this, and if you haven't, you should review it to make sure you understand that model before we talk about this model. It's just a circular model of your trigonometric functions, a pre-calculus 2 model.